starting to record.
All right, thanks team. Good morning, everyone. I see a lot of folks still coming in, more than hundreds. This is another fantastic talk at a hydraulic fracturing community Robe talk series. This series has been amazing ride, if you will, for everyone, including myself. We never thought we have so many people interested and engaged and entertained by such a wonderful group of speakers, including Tim himself today. And we want to thank everyone for participating, for being professional, especially for the speakers, past speakers, including Sid Green, Andy Bunger, Mark Robe, Gary Couples, and many more to come. This week we have Tim, Carr, as well as Joe Morris and the Fu Wei from Lawrence Livermore. So today, I can't say enough of this project. Last year we had fantastic talk from a team at New York, a hydraulic fracturing workshop organized by this community. And like Tim said, we pick up New York on purpose, actually, as we all know why. This project called Marcellus Shale Energy and the Environmental Laboratory is one of a kind. You may heard some other field experiments, but I have to say this is one of a kind. We are so blessed to have Tim to share, actually, as a matter of fact, the latest of latest results from this second phase. $26 million in situ field experiments that carried out by Tim and his team in West Virginia University in Marcellus. Speaking of Tim himself, Tim has been very distinguished career, I have to say. He's the department chair right now at University of West Virginia University Geology Department, as well as he has quite experience in both industries, starting back in ARCO days, all the way to academia. He and his research group, a pretty big group in West Virginia University, looking after this fantastic program. And he had actually Texas flavor too. Didn't realize Tim, you graduated from Texas Tech, which is a very nice school in Lubbock, and then he got his PhD in Wisconsin. So this he has been, I think, know many people in these participants that I do. So with that, I turn over to Tim. But before that, I want to acknowledge Tim again, because you don't need to do anything for this presentation, because Tim going to record and share the video afterwards. We didn't ask any presenter to release any, but those presenters, including Tim himself, are willing to share this with participants. And we will, as well as a PDF file for this presentation. So I will release those links in the next newsletter, upcoming newsletter. Stay tuned. If you didn't receive my newsletter this weekend, that means you are not on my email list. Send me an email. I will sign you up. We not encourage people forward meeting invite from both legal and copyright point of view. So with that, I turn over to Tim. Tim, feel free to take over. Thank you very much.
Okay, thank you. hang on. First thing is, as you said, I went to school at Texas Tech, Wisconsin, and I taught at Kansas for a while, in West Virginia, and now every one of those schools is after me for money. But this is what I refer to as the MSEEL project, and I see the first typo because I used this for a January update, this title slide. But and this is my NASCAR slide. Basically, I don't know if I do anything except try to keep everybody going in the same direction. So a lot of people, I put the researchers here from West Virginia University and BJ Carney from Northeast, and Rob Vignetti, who's I guess my project manager at NETL. And I can't forget that. Let's see here if I can get it to work now. Click, there we go. First thing is, this has got a lot of aspects. We work on the environment, surface impacts, emissions, the whole thing, but we're just going to concentrate on one thing, but it's a long-term collaborative field project. And so it's been, we'll just do it. It essentially got going in 2015. There's an interesting history there. And it's right across, the first part of it was right across from the city of Morgantown. You can see it in the background. Actually, you can see my office if you got really blow up there. So it's very close. And really, from that MSEEL-1, I'll refer to as the MIP, Morgantown Industrial Park, the importance of logging the lateral. We logged one of the laterals and really emphasized the geomechanical properties and the fractures, and that's what I'll talk about, getting that data. And then we did fiber optics on the 3H also, and then DAS and DTS. And we're still monitoring the DTS there at that project. MSEEL-2, which I'll talk about mainly, is sort of trying to do that in cost-effective manner, and also in a nearer to real time. And so we'll talk about the initial results and plans. I should have put it the other way around. Okay, here is MSEEL-1, started in 2015, December, when production started. And 2 wells were essentially drilled, the 3H and the 5H. There's 2 older wells, the 4 and the 6. And interesting thing about that, and I always make a point, is these 2 wells were protested pretty, at least the 4 and the 6 were protested by the city because we're a university community and it's right across the river from. And these wells supply all the gas for the city of Morgantown, about 100,000 customers probably in greater Morgantown. And so when I go to the farmer's market with my wife, is to, buy local. So, but we recognize a lot of fractures in the 3H, about a little over 1,600. Use some of the geomechanical logs. We really didn't use the image logs, and we should have. But we learned a lot from the DAS and the DTS about uneven stimulation. And there's been continued testing on that, as I mentioned. And there's fracture modeling that we worked on, and there's work with Los Alamos going on right now. And I know Hari's online. The data is available. It is public domain data. And there's numerous projects going on. I just reviewed a paper. I had no idea that they used our data and had submitted the paper to SPE, Reservoir Characterization. But I won't talk about that since I can maintain confidentiality for it. The Boggess site is about 7.5 miles away. There's a lot of advantages there, but really, how can we leverage the understanding we had made at MSEEL-1 to drill better wells with more gas, minimal risk, similar lower costs. Testing next generation cost-effective technologies, and try something that you can maybe use on an every well basis, and try to work toward, I would say, more real-time intervention. and improve the completion and fractures and fracturing stimulation. And really looking at the natural and induced fracturing and the unconventional fracture modeling. I stole this from Andrew Bunger, he may be on, but without permission. But what we're really just trying to do is move that Pareto optimum a little bit. I don't think we can move it that much, but see if we can move that curve that you could get more gas out at lower costs. One thing I want to emphasize, that these wells out here, some of them are 13,000 feet. You can't, the geology of the Marcellus changes at a much higher frequency than 13,000 feet. You can't stay, one bed doesn't even stay the same. And the number of fractures, these are Terry Engler's pictures from New York, but I've stood on that outcrop. I think everybody that's been up in New York has. And so this is what you can see and I got another picture. Here's another picture of the Marcellus right at Riscony Falls. And the bedding, it's not a uniform formation. And that's one thing to be looked at. So MSEEL-1, they have about Northeast has about a 4-foot target, and they stay in that 4-foot target most of the time. But the geology of that 4-foot target changes, is what the bottom line is. So this is showing the 3 and the 5, sort of drilling up a little bit of an anticline, not much. It's pretty darn flat if you looked at the depths there. But you can see that that's where they landed the lateral. And we did a lot of microseismic there. And this is sort of a bit of a puzzle to me. We had a vertical well for monitoring. So we pretty should have quite good depth control. And you can see that the microseismic goes in the north 59 east direction. So remember that. But also that the microseismic is well above the target horizon. But yet these are great wells. It's up in the non-organic Montango is where most of it is. It ends at the Tully. And you can see that that's most of the microseismic up there. We logged the lateral, and the first thing is lots of fractures. So here's the fractures, more than 1,600 fractures. Here's a blow up of it. You can see that they cluster. One other thing is you can see that the fractures go in basically an east-west direction, north 85 east. And then we had 28 stages, which we divided up into, and that was probably a bit of a mistake, but we had 2 geometrics. We had a engineered, tried some different chemicals, frac chemicals, and then sort of did a variety of things in the last number of stages. But you can also see the number of fractures varies quite a bit. Here's my favorite one, stage 10, has 160 fractures. But you can see that they do have a lot of fractures per stage. Those fractures, and this is Natalie's work, we're seeing those fractures everywhere. And they're basically self-fractured, got lots of dead oil, bitumen in them. You can see that along this side of here of this fracture. You can also see little bitumen through fractures going in a different direction here. And these are sort of oblique fractures. And this is not the only well, but when we start looking at them, we see these things. These are from probably when the rock matured, late Permian be my guess. And you can see those. And they're all calcite filled, which is great because we can image those fractures beautifully. with both the electrical imager, and that's what this was here, QuantaGeo, Schlumberger's QuantaGeo. And then the other thing is all these fractures will fail. They're quite weak. In fact, if you try to test, the rock just falls apart on those fractures half the time. They're just weak cements coming in there. This just shows, this is Caitlin Evans' work. We can see the difference in the different formations. The Tully is a nice fracture barrier. Here, this is Poisson's ratio versus Young's modulus. We could, the same, if you compute SH min, which is basically Poisson's ratios times BO is constant, the plot looks pretty much the same. And you can see that it's up in a quadrant that probably is sort of a little more plastic, but also fairly strong. The Huntersville chert is in more little brittle and strong, and and if you don't have the Onondaga, which is all of southern West Virginia below you, you're going to fracture right into the Onondaga and get the ocean. So that's sort of an interesting to get this thin Onondaga here. The Marcellus sits right down here, and the Montangle comes down, which is the non-organic part of the Hamilton group. And you can look at that on a stage basis. So this is Caitlin again. This is stage 10. So fractures in the little green dots here, there are a lot of them. Here, this was done geometrically, 200-foot stage, put the 5 clusters in, and you can see that there's quite a change in the Young's modulus, quite a change even in the Poisson's ratio in between along the boundary there. And there is a couple little faults right through here. And they probably, soft sediment faults, probably what they are. I have no idea. But if you plot stage 10 on that same quadrant of Young's modulus versus Poisson's ratio, you see the distribution here, and it's not very tight. There's quite a difference in both the Poisson's ratio and Young's modulus by depth. So here's just the depth plot here on this side, and you can see that going, changing quite a bit. Well, that led to what on the DAS was, and this is the DAS amplitude right here, and you can see that it led to the fact that it'd be cluster 5, 1, and 2, but even 5 is the big culprit, was the one that broke down and takes all the energy. And this wasn't the clusters in between 2 and 3, I guess 3 and 4, excuse me, really didn't get activated whatsoever. So it wasn't a very even cluster. And I just have an animation, and you'll see that it's very uneven here in terms of energy. You also see that the temperature goes way up on the stage that's got a bridge plug. So we're getting communication out through the formation, not through the bridge plug, or else it would cool. And you can see again that it's a very uneven stimulation. We've done work with that. This is Payam's work, taking a look at the temperature. And in fact, if you do it right and change your color scale on your DTS, you see that warming in the previous stage. And we can also see that on some of the attributes that we're taking a look at. This is instantaneous frequency. You can see it change right in here, and even in here when you've seen that temperature again. And then this is, we can see that change with the DAS attributes and the DTS. If you look at one that was engineered, just luckily, you can see that it's got a much tighter distribution on Young's modulus and even Poisson's ratio. It doesn't go whipping up through here. So you can engineer these a little more effectively. And again, you'll see that the tongues are much more even here. And also the temperature doesn't really change at all in the previous stage whatsoever. Just minor amounts. Okay, and that's again shown on here. You can see the cooling, and here's the energy, quite a bit more even in terms of. So that got us thinking, well, what's going on? And here's a little cartoon model. The microseismic is following SH max, no question. That's where every well in Appalachian Basin tends to do that, as far as I know. But what happens is we have these fractures that are running east-west, north 85, and we're seeing that warming in the previous stage because the well's a little oblique to it. So there is communication through the formation. So that got us thinking the importance of fractures. This is the long-term DTS, and things you can see is the fact that the engineered stages are cooler. Or warmer actually, and so we got we could see some things going on there. MSEEL-2 drilling started in 18, completed in July. 6 wells on the pad. We had the permanent fiber and the 5H right in the middle, that red star. And we had intervention fiber in the 1H. And so we could monitor DAS and microseismic. So, and then 2 of the wells, an outside well and an inside well, were geometric every 200 feet. 2 wells were designed by someone else using basically the geomechanical properties. And so that would have been the 5H itself with the permanent fiber and the, 15H. And then we ended up designing 2 of the wells, the 3H and the 1H. We did not have complete data on the 1H, but we did have complete data on the 3H. We have a core, and I wish I could talk a little bit more about it, but that's down in at TerraTech Schlumberger in Houston. That's taken a little more time to get looked at because of COVID and moving that core. So we do have the core, and we have the vibrational data, the fracture ID data, and a complete log suite. So that's being looked at right now. Sort of what I want to talk about is we logged the 6 laterals with an acoustic image log, NABORS / Petramar log frac view. And we also had the vibrational data, the frac ID type data in the laterals too. So we use that in our design of the 3H and 1H. First thing is, I could have put any of this is the 3. Every one of these wells got a lot of fractures. And these are the ones they picked up. So these will be the large ones. And I think you can see, here's the image logs. I mean, I can even do these, but they're independently picked by Dr. Lee down in Houston. And so this was done by him, and we have all the wells. So completion. One thing, the 5H has the permanent fiber. So this is Slex's permanent fiber. And this is the DAS data for stage 5 of that well. And what you're going to see is it's a very, very uneven stimulation. There's 4 clusters that were picked. And you can see, quote unquote, the amount of computed sand and proppant and slurry that were put into there. And you can also see that that's very uneven. Maybe we'll just, oops, go here. Here's a little different way of looking at it. Same thing, and let me go to here. Here's a different way of looking at it. we took a look at this, and we looked at it, and there's SHMIN, and it's computed. There is the fracture intensity. And you can see that cluster 4 and cluster 1 are associated with highly intense set of fractures, and they take most of the energy. And so very uneven stimulation there in that stage. And then you can do the same thing with this is stage 10, luck of the draw. They're a lot more even as far as the waterfall plots up here. You can see that quite nicely. Not completely, but pretty good. And if we take a look at the fractures, I would say the fractures are just about everywhere, and they tended to put them in the fractures. So I guess that's good, but SHMIN is a little different, and that associates with cluster 4 having a little bit more energy. I'm just going to show lots of work to do. We haven't really done anything. Oops. We do have lots of microseismic and working on that, and the microseismic behaves like you should think it behave in that north 59, 60 degrees. But there's a lot going on there. And so you can see this is for just a selected number of stages. We got a lot more microseismic data to work with, almost too much, I'll tell Selexa. But hey, you can never have too much. Here is where they designed on the SHMIN, I guess, and we can see here's the fracture density from from the vibrational data. Here's the frac from the view data, so frac view data, and you can see that they're putting it right in where we would not. We tend the whole way we would have done it is, and the way I'll show you we did, is we stay away from the fractures because we want to, and we find a consistent SHMIN. So we bin SHMIN. This is all Way's work, and I should put her name down here. And then we grade it. So these are our grades on the end, our completion grades. So this just shows how we did the 3H, staying away from the fractures as best we could. We varied the length of the stages, 170 to 230, I believe, but right around 200 most of the time, and try to maintain 4 or 5 clusters and try to hit these grades. And we can talk about that, but there's weights assigned to it based on the vibrational data, MSE, things like that, the SHMIN, and also probably the biggest weight is on the staying away from the fractures. And that comes down to the fact that what I think is once you start these things, be it a fault or a fracture, it's just going to keep on going. And I've seen that when they cross faults, but I think this really progresses on that too. Let me get back on the page here. So trying to put together a learning model, and this is Loe, using both the drilling data, the frac view data, and the frac ID data and try to see how thin we can go to a data set to try to come up with a more automated type of machine learning. So this is work that's under right now. Okay, so production. Production just started at the end of this year. So we do have fiber in the 5H. Unfortunately, that fiber is non-functional, below 13.5, but we do have quite a bit. And so they monitored DAS and DTS, and I just got some of the initial results. Here's some initial results of the DAS mapping that was started and still being looked at. And you can see the different stages there. And as the production begins, and here's some here's a frequency type map of DAS with the different stages. and starting to pull some things out. Lots of processing to do. I don't have any answers here for you, but we got it. What I do have is I can take that 3H and that 1H, 3H being the primary well that we did, and you can look at the production. They're longer wells, so that's not a very fair comparison, but you can see it starting in mid-November, the production. If I put it on a 1,000-foot basis, this is fair. You can see that the 3H's, which is the one we had all the data, we didn't have frac ID on the 1H, is the best of the interior wells. You can also see that the 2 edge wells are the most effective wells. They're not competing with each other, but the 3H is now producing anywhere from about 10 MCF to 20 MCF per 1,000 more, which not a lot of money, but when you got a 13,000-foot well, it sort of adds up. And also I can see that the 1H is starting to catch up, and we'll see if it does with the 17H. The data, MIP data, it's available. You can get online right now, and we have DAS, DTS. Be prepared for a slow download on that. Lots of logs, whatever. And if it's not there, let me know. Constantly finding. The Boggess well, we got a lot more data. We're about 108 terabytes, and that's going to be a challenge to serve that data. That data will be available a year after production began. So let's say at the end of this year. Okay, lots of work. This is all premature. We're working on the fiber optic data, both from the DAS, DTS, and also the microseismic. The core analysis is underway as I speak, down at TerraTech, and then they'll come back up here for XRF and some other things that we'll do. Building a unconventional fracture model using all that data. Trying to come up with some artificial neural network models that I mentioned, mainly for you could target these, to use the data that you get from the LWD logs to target those. And I think we can do it by hand. It's not that hard, but it would be better if we could do it a little more automated. And we're doing long-term reservoir modeling with DTS, and we're going out picking up that data. And then I think there's a lot to do, and that gets back to Andy's thing, is to look at the economics of this. Is the engineer completion worthwhile? And I think it is, because I think the geology changes in 13,000 foot along these outcrops significantly, both geomechanically, lithologically, and we need to take that into consideration. And then we'll start, this the whole thing with the lab is to leverage all the smarter people out there than I am. I'm just a dumb geologist, and let them at it. So it's the data will be made available. That's the sort of the beauty of the lab. And also then you can also replicate and test other people's conclusions. And so that's, and come up with the right answer. So that's where we're working on. I'll just end with that. This has been an interesting project. It'll end in March 20, not less than a year from now, March 2021. And we got a lot of work to do, and maybe get an extension since we've been a little bit dead in the water here for a couple months. But it's nicely funded by DOE, but lots of cooperating industrial, a lot of academia cooperating actually everywhere. I got people looking at chemistry of the frac fluids, the bugs, organic life that is introduced in multiple universities, Ohio State, Vermont, Colorado State. So there's a lot going on. And so I think with that, I can stop right there.
Thanks, Tim. Have to see this. This is a very advanced from last year you shared from New York, and a lot of good work and progress. And I see people already asking a lot of questions. That shows the interest. And congratulations, Tim. You are one of the speakers that attract most of the attendance so far. So with that, I think for the folks who ask some questions, I saw how to join this newsletter. Whoever forwarded you the meeting invite may have my email address. If not, my email address is gang, G-A-N-G .han, H-A-N, at aramcoamericas.com. I always use this, okay? I'm not a guy, so it's pronounced as a gang, not a guy. But nevertheless, open the floor for Tim. And Tim, our presentation, the Robe talks about 45 minutes, but today's Zoom is hosted by Tim and West Virginia University. So feel free, Tim, to stay as long as you could. And but the Robe talk itself is 45 minutes, which means we scheduled probably another 10 minutes of Q&A. But I'm sure the questions you asked that Tim couldn't answer within this seminar, he will might be able to follow up afterwards. I heard previously Zoom has a function that Tim, before you close Zoom today, there is a function where you can output the Q&A sessions so that you can read the questions afterwards. But nevertheless, Tim, feel free to address any questions you see from the chat window.
Well, I see Andy gave me permission. That's good. Karen asked how many perforations. And the size, and I don't know the size of the perforations and numbers. I don't know if Phoebe is online or not, but and also it varied if we had with the fiber too. We changed that a little bit too. See, Mark Zobak, have you tried to calibrate the computed SH mins with the DFIDs or the mini frac? We have calculating SH min, and we just use the SH min as calculated for us, and I'm sure it is problematic, but and then we calculated some other things, and that's we do have the those, and it's a good thing to do. That need to go back and take a look at that. Did the second experiment use 50 perfs like the first experiment? There's essentially 4 or 5 clusters. So if there's, it depends how many clusters there are, and I can get the, it depends. It depends. So, and Young's modulus shows a direct relation with Poisson's ratio, while the opposite is usually expected. Direct positive relationship, I mean, there appears to be a relationship moving up to the carbonate, and I guess that's probably expected, because we do get in the Marcellus variable amounts of carbonate in the, because it moves up toward the Tully and the Onondaga. I think you'd expect that to happen in terms of how carbonate reacts as far as Poisson's ratio, but also you got density in Young's modulus, so that's going to change 2.71 versus 2.64. It's going to change quite a bit too. I'm probably getting more questions faster than I can answer these. Ivo, aside fiber optics and some proppant monitoring, did you guys consider using frac diagnostics, production logging, tracers? Yes. Production logging we did, and that's available on the MIP site. We did production logging, I want to say about a year after the MIP 3H was completed. We probably could do it if we can find the money. We did try some tracers, some unique tracers, which exploding proppant, how's that? Really imploding proppant, which I don't think worked, but we listened, Selexa listened for a long time. Yeah, I think the thing about comparing to the mini frac and the DFIDs is similar to Mark Zobek's question. 3H was not engineered to stay away from the fractures. Well, the 3H at Boggess, I was going back to MIP. Well, I think the 5H, they did stimulate some of the fractures, if just accidentally. I don't know if you want to call it accidentally or randomly. They put the clusters right in the fractures, and then when they did that, the fractures took all the fluid. I guess if you want all your and sand, if you want all your fluid and sand to go through one of your clusters, that could be, but actually the 3H is better by production than the 5H. So 5H was sort of a little bit of a mixed bag, so it's not a direct experiment. Is the data open source? It will be open source. There's plenty of log data on there from the MIP site in terms of basically the log data, and there is some core data too. So I'll skip Jay Hewlett. The answer is there. It's where the data is. It's on MSEEL.org. You look under data. Well, yeah, it could be from logs. Yes. It'd be physics-based instead of just neural network. Yes. We got lots of work to do. This is not a results thing. What kind of production have you seen with respect to the low pop concentration clusters due to natural fraction? Milton's question. I don't quite know how to answer that. And Karen, I can type my email in the chat box at the end here. Maybe I can get down to the bottom. I will put the PDFs of the slides out on the web. I'll send that to ARMA. Yes, the clusters lose energy and change during the frac job. Yes. There's all kinds of variations. There's there should be the pumping completion report should be there. This is Oslin. And there should be the completion report should be out there. And send me an email. I can. MCO1, Craig Edmonds. How deep was the monitoring well array? It went all the way down to the. I think the array was all the way down to the Marcellus, maybe right above it. Oh, as far as the MSEEL-2 wells, yes, it's done with a microseismic array. So no geophone array. Wish we could have done both. Need more money. Have you seen that what you didn't expect or what you have observed that you don't have a good explanation for yet? I don't have a good explanation for most everything there. But I think we got ideas. And I'm going to type my email in here too. Well, I want to thank anybody. Anybody else have any other questions? I just sort of went down through the chat. Is there any data measured for the pressure at the upstream of the choke? Yes, there's pressure data in the production data.
Yeah, Tim, thanks for the email. For the folks who are looking for the presentation, when we release the newsletter, Tim's email will be in that newsletter too. You might find